look at one more thing, one last building block that we need before we can look at this. So I think by the end of today we'll have all the building blocks so that we can start this right up on Tuesday when we come in. This will sort of give you an idea of what's going to happen a little bit later on. Let's say we have some rigid body. And just to make life somewhat easy, I'll just sketch some general shaped rigid body here. Let's say that we apply a single force. So I said I'll make life easy. We'll just consider one force here. Let's say we apply a force, we call it F, and we apply it at this point right here. And let's say that for some reason, whatever the case might be, there's another point of interest in the rigid body over here. Okay? If you want to give the point a name, you want to call one point A, one point B, fine. Okay? It's not going to matter too much here. So let's say we have the rigid body, and there's these 2 points of interest, and let's say we apply the force at the one that I've shown it at. There's going to be some effect on the rigid body. Okay? Might want to make the body translate and rotate some kind of way. Maybe I want to apply a force at the other point though, but I want to have the same effect on the rigid body. I want the rigid body to behave in the same way. In other words, I want it to translate and rotate the same way that I see right now. Now obviously just moving this force, if I just move the force and that's all I do, what I observe is going to be different. Okay, and I illustrated that to you before. You know, it doesn't work too good because there's too much friction between this and the glass. But if I apply a force at one point out here, I get one kind of movement. If I apply the same exact force at another point, I get a different kind of movement. Okay, but what I want to do is I want to take that force, I want to apply it to a different point, but I still want to observe the same movement. Okay, so obviously something else is going to have to come into the picture here, because if I take the force and apply it at point A, and then move that force and apply it at point B, I get a different movement. So I'm going to need something else that affects this rigid body in order to keep the motion the same. So let's see what we can do. Let's try this. It's supposed to be the same rigid body. And here's the force that we currently have applied. And here's our other point of interest over here. So this one's F. Now tell me if the equals here is true if I do this. If I add 2 more forces into the picture, yes. Is the rigid body going to behave in the same way?
Yes.
Yes. Yeah, because this force and this force will essentially cancel each other out. Did I say that right? No. The 2 blue forces cancel each other out. Say this is what happens when it gets late in the day. The 2 blue forces cancel each other out. And so what's left is the red force, just like we see in the first picture. Okay? Now let's take this one step further. Now, here's where we want to look at these 2 forces. What do these 2 forces represent? Force couple, because equal magnitudes, parallel lines of action, opposite sense. So I can take this force couple, and remember, I can find the moment of that force couple because the only thing a force couple wants to do is create rotation. So I can find the moment of that force couple, and let's say I apply the moment here. Remember, it's the same no matter which point I apply it to. So what's going to happen now? Well, here's the point that we had before. Here's the new point. We still have this force F that we added to that point, but now I'm taking these two forces and I'm going to find their moment, like I said, about any point, but I'll make it this point, and I'm going to get some moment vector result. We do that cross product, we get a moment vector result. That moment vector is going to look something like this, so that's the moment. And if you see this kind of symbol here, okay, I don't know if we've seen it before or not. If you see this moment vector, you know it's a moment vector because it's got that spinning line around it, telling you that this is not a force, but this is a force couple that has generated this moment vector. And oftentimes when we have free body diagrams like this, where we're showing the rigid body and all the forces that are acting on it, when there's a force couple, like we've got here with F and minus F, oftentimes we don't show the two forces because the net effect in the translation aspect of motion is a cancellation. Okay? If you're just concerned about translating the rigid body, this force and this force will cancel each other out. What they do, though, is generate a moment that would want to create some rotation. So rather than show the two forces from the force couple in a free body diagram, oftentimes what we show is their moment vector. And we know it's a moment vector because of the spinning arrow around the stem of the arrow. So when you see this, if I were to ask you how many forces are being applied to the rigid body, you should not say 2. You should not say 1. You should say 3. Because this moment vector represents a force couple, which is 2 forces, and then you've got this one as well. So notice what has to happen. If we have the original picture where we apply a single force at the red point, and we want to apply the same force at the blue point, but we still want the motion of the object to be the same, we're not only going to have to apply that force at the blue point, but we're also going to have to apply a force couple somewhere on the rigid body that creates this moment. And why does it have to be that way? Well, you saw what happened when I demonstrated here. If I take my force and I apply it to the red point, point number 1 out here, I get some counterclockwise rotation. If I take the same exact force and apply it at my new point, I get clockwise rotation. Well, what do I have to do if I want the motion to be the same as the original? Not only do I apply this force here, but I also apply a moment that is strong enough to overcome the rotation, the clockwise rotation that my force wants to exert, so ultimately I get the counterclockwise. So watch what I have to do. Exert the force, and at the same time, exert a moment, so that I still get that original motion. So we can move the point of application for our force to any other point on the rigid body as long as we add in the appropriate moment to keep the rotation aspect of the object's motion the same. Okay, from a translation point of view, it will still translate the same way up and to the right, but if we want it to rotate the same way, we need to add the appropriate moment in to account for the changing of the point of application. So where we're heading with this next week is we're going to have a rigid body that might have several forces acting on a rigid body, acting on the body. And we might want to say, okay, rather than look at this rigid body with 3 or 4 or 5 forces acting on it, because it's kind of hard to see how a body will behave if you just see 5 separate forces all going different ways with different magnitudes. Is there a way we can reduce that picture down so that we just have a single force and a single moment acting at a single point? So So let's just see if we can do one quick example here, just so that you see this worked out in a more concrete scenario. This one will be from our book. We'll take 3.79. Okay, and this picture here, by the way, this is what we would call an equivalent force couple system. It's a force in a couple that has the same effect, equivalent effect, as the original system. Okay? Now this is the most basic case where you would just have one force. Like I said, what we really want to work towards, and we'll see this on Tuesday, is what happens when there's multiple forces. Because when you just have one force acting on the rigid body, you can visualize without too much difficulty the effect that it's going to have. When I had the eraser and I just apply a force, you kind of know what it's going to do. But if I applied 5 or 6 or 7 different forces to the eraser, now you might not know what it's going to do. But if you can reduce it down to this kind of picture with one force in one moment, then you might have a better idea. So anyways, 3.79. We want to find for this rigid body, okay, so if you see it in the book, this is some kind of, it might be like a shelf bracket that's nailed into the wall. And so you would have 2 of these things. You might have one here, you might have another one here, and then you could put a shelf coming across. Okay, so we have one of these shelf brackets, and maybe the shelf, or maybe we set something on it, whatever the case is. Maybe, maybe somebody's just grabbing the end here and they're just pulling down 135 newtons. It's going to have some effect on this rigid body. We want to replace that single force with an equivalent force couple system at B. In other words, we want, if I take the same picture here, so here's the point A, B, and C. So here's point A, B, and C. I want to apply some force at the point B along with some moment, so that the way the rigid body behaves in the left-hand picture is exactly the same as it behaves in the right-hand picture. So the way I do this, the way I find these equivalent force couple systems, when it says find an equivalent force couple system at B, I say, okay, well, there is going to be a force at B that could potentially have an X and a Y component. So I'll put my FBX and FBY components there. And I'm going to have to put a force couple into the picture, represented by a moment vector, to account for the change in the rotation, like I showed you with the eraser. So what I might do here is I might draw a moment vector and call this one MB. Now because this is 2 dimensions, the moment vector would actually be coming straight out towards you. Okay? Remember, when we're working in the XY plane, all the rotation has to be about an axis that would be parallel to the Z-axis, so that means coming straight out towards you. So you don't see the arrow, you just see the spinning circle around the arrow, okay, when you're looking straight in. So that's what that represents. Now this equal sign here means 2 things have to be true. The sum of the forces in the left-hand side has to equal the sum of the forces in the right-hand side. Okay, so this equal sign here tells us 2 things. The sum of the forces in the left-hand side equals the sum of the forces in the right-hand side. Also tells us that the sum of the moments around any point in the left-hand side has to equal the sum of the moments around the same point in the right-hand side. In order for that equals to be truly equals, those 2 conditions have to be met. This accounts for making sure that the translation aspect of the motion is the same, and the second condition makes sure that we have the same rotation effect when we change the way the force is applied. So taking the first condition, the sum of the forces in the left-hand picture equals the sum of the forces in the right-hand picture. Let's take the x direction. So if I look at what's happening in the x direction, nothing in the left-hand picture, equal to FBX in the right-hand picture. Okay, so guess what? I know FBX now. Take the sum of the forces in the y direction, negative 135, equal to FBY. So if FBX is 0 and if FBY is negative 135, what do I get here? I get FB equal to 135 newtons going straight down. Okay? Now this says find equivalent force couple system. There's two parts to the answer. You need the force that's being applied at the new point. Okay, and like I kind of illustrated here, when there's only one force involved, it's going to end up being the same force. So it doesn't surprise me that we get 135 straight down because that was the original force. But we also have to put in this moment vector. And like I said, in 2 dimensions, that moment vector is coming straight out towards you. That's why you don't see this arrow, you just see the spinning arrow. Okay? So let's take the sum of the moments around the point B. You can choose any point, because that's what it says, the sum of the moments around any point. So I'm choosing the point B. So if I look in the left-hand picture, hold the point B fixed, counterclockwise rotation, I get 135 times perpendicular distance. I'm going to convert it to meters and say 0.125. Equal to the moments around the point B in the second picture. Well, the force components don't create any moments around the point B because their lines of action go through the point B. But remember, we had to introduce a force couple somewhere into this picture that has a moment called MB. So if we were to take the moment of that force couple around the point B, or any other point, we would get MB. And since I showed it as counterclockwise, it's positive MB in my equation. So now I get MB equal to, let's see, when I multiply this out, I get 16.9, and that's Newton meters. Now, moment vectors are vectors, so I need to put this in vector form and say the moment around the point B is 16.9 Newton meters, positive counterclockwise rotation. Okay, or I should say positive means it's the same as what I showed in my picture, which is counterclockwise, so I have counterclockwise arrow here. So my equivalent force couple system is this force and this moment. So if I have a force 135 newtons acting straight down on the point A, and I want to take that force away and apply a force at B, but still have the same effect on the rigid body, I can apply that 135 newtons straight down at the point B, but I'm going to have to add a force couple in somewhere that creates this moment so that the rotation of the shelf bracket, whatever it is, would be the same. Okay? You see, if we held the point B fixed here and we push down on A, we get rotation. If we held the point B fixed here and the only thing we did was apply the force straight down, we would get no rotation. That's why we had to add the moment in to make sure we still get the rotation. All right, so that's just a preview of what we're going to do on Tuesday. Like I said, Tuesday we're going to take this up to the next level where we have more than one force. So let's say we had a force here and a force here and a force here and a force here. And we wanted to reduce it down to a single force and couple at B. How would we do that? That's what we'll see. So let's say as far as homework goes, I'll give you a break. I want you to just go back over all the homework we've had so far in Chapter 3, make sure you understand all of those problems that have been assigned. Okay, chapter 3 is a big chapter, so I want you to take the advantage of the opportunity I'm giving you here to make sure that you really understand everything we've done up to this point. Okay? So no new homework. The sign-in sheet, that one make its way around.